Well, good morning. I'm Mike Koets from Southwest Research Institute. I'm going to be talking today about solid-state recorder data organization software and functional emulator for mission planning and early integration. One of my colleagues pointed out that I probably could have fit one or two additional small words in that title, but I couldn't find good ones, and so we're stuck with this. So what I'm primarily talking about here today, by way of an extended example, is an approach for developing software for complex but encapsulated components. So it's complex functionality hidden behind a fairly narrow, fairly well-defined set of access methods, an API. With various benefits I'll talk about, but that's fundamentally what I'm going to be talking about and sort of in this context of the solid-state recorder application. We have used this approach for a couple of different applications, one of which is the solid-state recorder, but also previously we've used this approach to develop the data link layer software for an inter-satellite radio link. Those of you who've been coming to this conference for a while, I talked about that a couple of years ago when we were in San Antonio. But the approach has a number of benefits. The key of one of those is early integration with the application software. So we have some fairly complicated functionality that's bundled up into a component and will be used as a service by larger software to achieve some larger mission. This approach lets us prototype this very quick, very early, and let the integration with that larger software system begin. Kind of in the same vein, it's responsive to changes in both the internal functionality of the components, but also the interface to it. Kind of as a peripheral benefit, we do get some early testing of actual flight software, flight code. And also by using this approach, we kind of do enforce an abstraction and isolation. It's so easy to, as the project evolves, add more functionality, more interfaces, and kind of make your design much more complex. This approach kind of helps us stick with a nice encapsulated software approach. So the extended kind of example we'll be talking about is the solid-state recorder. The diagram on the right kind of gives a very notional block diagram of the hardware components involved in one of these recorders. But it is a very high-performance, non-volatile memory system that the ones we've been developing call for multiple terabits of non-volatile flash memory, multiple data streams coming into the recorder. Each of those data streams may be running at several gigabits per second. Also, we have multiple data streams leaving the recorder, also at multiple gigabits per second, and all of that can be happening simultaneously. So it's a pretty complicated, pretty high-performance data management problem. And in addition, we are using flash memory, which brings some unique constraints to it, different from standard random access memory. A key one is a slow programming rate, as well as asymmetric access rate. So while it takes a while to program, also we can read out at a very different rate. And so when we're trying to balance these data flows, we have to address that asymmetry. Another key constraint is the block organization of flash memory. Flash memory, at least in these volumes, is typically NAND flash memory that can only be erased in relatively large chunks of memory. So that adds another layer of management. And there's some additional issues with flash memory we'll talk about a little later on, too. So the data organization software is part of the solid-state recorder. It's not the whole solution. But it kind of works at the highest level, and it's the layer of functionality that interfaces with the users of the solid-state recorder. So its job, its function, is to associate application-level data items with physical storage locations. So the user is going to do a data collection, perhaps to collect an image or make a synthetic aperture radar observation. And they want to store it in the flash recorder, identify its bounds, and be able to retrieve it later once or twice, erase it when they're done with it. So the software manages that association, keeps track of where those application-level data items live within the physical memory. And so as part of doing that, it manages the addresses for recording, playback, and erasure. It provides control interfaces to the spacecraft application. And in addition, it provides status information and telemetry, again, to the users and to the spacecraft. So this software, this data organization software that performs these functions, executes on a single board computer within the solid-state recorder. So it's a dedicated processor, relatively resource constrained, but generally all ours. And it interfaces with the application software via some physical communication link, like mil standard 1553 bus, for example. Alternatively, this software could execute in a larger processor with other application software and interface directly with the memory banks. So our data organization software provides these kind of, or works kind of in this way. The diagram is just a very notional illustration of it. The SSR is used in a couple of different ways. One might be a very simple FIFO, where data is recorded, stored for a while, retrieved in the order it was stored, and erased once it's been retrieved. A much more common and more complicated usage scenario is a sort of simplified file system where individual data items are stored and retrieved in a more or less random access sort of way. Now, it is the file system type functionality we provide in our software is quite simplified. We don't provide all the services you would get out of a Windows or a Linux file system, but does provide a little bit more flexibility than a simple first in, first out data organization. We also manage multiple independent data stores, so essentially analogous to different hard drives. But the idea here is that you may have multiple sensors providing data, and the amount of data involved and the size of the flash memory we can provide means we have multiple different physical and logical storage spaces for the different kinds of data. Within each of those data stores, within each of those drive analogs, we provide a number of partitions. Currently, our software provides 1 to 4. These are analogous to a partition on a hard drive. And the idea is to carve out a dedicated space for storing some kind of data, some classes of data that's isolated from other storage and dedicated for that use. There are contiguous regions within the flash memory. Each partition is managed at some level as a FIFO. So data is written to one end of the FIFO, and data is erased from the other end of the FIFO. But we provide a little bit more flexibility in how data can be read out. So within a partition, we have the concept of records. This is analogous to a file in a traditional file system. Again, there are contiguous regions within a partition, modulo rolling over the boundaries of the partition. Data is stored and read from these records. But we do provide random access to the records. So data can be read out from records in any order, and also can be read out from part of a record. Because of the limitations of flash memory and the amounts of data of memory involved and the rates we're accessing it, our hardware architecture imposes a fairly substantial storage granularity. Typically, this runs to several megabytes or several tens of megabytes. This is a consequence of both the inherent block structure within each flash memory component, but also the fact that we're operating a lot of these flash components in parallel, and so we have sort of parallel blocks. So that's something else we have to manage. Within each of these data stores, then, we have a logical address space of 4096 storage units. That's just how the hardware mapping comes out. So that's how we organize the data. This is a view of the API we provide from the solid-state recorder to the applications and the rest of the spacecraft that are using it. It's a fairly simple API. Here's a list of the commands. We can create a new record and write data to it, close it once we've finished writing to it. We can read data from the record, either an entire record or some portion of the record. We can erase data from a record. So this is where we partially remove a record. We read data from it and shorten it to free up space in the recorder without completely removing the record. Or we can completely remove the record. And then provide various forms of status information to the spacecraft or the other applications to identify how much space is available, what records are there, their sizes, other information like that. So in addition to these functional considerations, our data organization software provides a number of other services or functions that are related to closer to the actual physical hardware that's used, specifically the details of flash memory. One of these is wear leveling. All flash memories have a limited endurance to programming and erasure, and so you do not wish to use one particular region of flash memory over and over and over again, as it will wear out and fail. And you'd rather spread those accesses around. And so the data organization software, in the process of managing the data storage and retrieval for the application, tries to spread that around the flash memory and level the wear on it. We also perform state logging. So as we create records, delete records, they grow and shrink. We'd like to keep track of which records are used and how those map into the flash memory, and store it in the flash memory itself so that if we have an unexpected reset or a power failure, when the system restarts, we can recover that information, reconstruct our state as far as which records are there. We do that using a log-oriented file system concepts so that we keep a continuous rolling log that moves through the flash memory of what the current state of the data organization software is. We tag those with sequence numbers so we know which one is most current. It lets us scan the memory and reconstruct that without resorting to a dedicated file allocation table or some region that might wear out due to the limited lifetime of flash. Another flash idiosyncrasy that we have to deal with is bad blocks. Most flash components, chips, come from the factory with some of their capacity broken, maybe only 1 or 2 blocks, but it's usually a little. And it's entirely possible for a few more of those blocks to fail during operation. Those failures are isolated. They can be worked around, but they are kind of inevitable. And so our software needs to keep track of which blocks have failed, monitor when blocks fail during operation, and then work around that, map around those bad blocks. And so that our API provides a transparent interface to the application software. The application software doesn't need to worry about those localized failures. It just has a consistent and continuous address space that it's working with. Our software deals with mapping around those bad blocks. So that was a sort of whirlwind tour of what the solid-state recorder data organization software that we have for our systems does. Now I want to get a little bit more into the emulator side and the development process that the talk is really about. So we have a software emulator, and it's a tool that supports the integration of the SSR into mission design. So this tool executes in a PC environment and lets us model mission activities as they relate to the operation of the solid-state recorder and characterize performance. For example, we can do things like plan the sizes of the partitions in our system and monitor recording sizes. What this does is it provides a platform for very early integration of mission-level flight software. So this tool runs in a PC environment, uses our software. We can start doing this mission integration very early before we've built any hardware, while the mission activities are still in the planning phases. So as the observation schedule is being planned, as the orbits are still being refined, and we can start executing the mission in the context of the solid-state recorder and make sure that it's going to do what it needs to do. And if changes need to be made, we can start making them very early before we've committed to hardware or committed to mission activities. Also, it aids in the discovery of any additional capabilities that might help the mission, additional interfaces to the data storage unit that we could incorporate that would make it easier for the application. So the structure of our software emulator incorporates the data organization logic implementation that is the flight code. So we are, from the get-go, executing and exercising the flight software for this layer of the operations, for the management of the data. And then we wrap that with additional simulation classes that model the other aspects of the SSR behavior in response to high-level mission operations, recordings, and transmission opportunities. So this diagram is sort of a visual view of this concept. So on the left, you see sort of our custom stack for the solid-state recorder application. At the top, we have the API, which is accessed by carrying messages over like a 1553 bus. That goes to the actual data organization logic, which in turn talks to the individual flash memory boards, the hardware boards that do the actual data storage. And then several layers of control for that down to the actual hardware. And then independent, by a separate interface, we have the data interface, because we are talking about gigabit per second data streams, several of them multi-directional, so it's a different hardware path. So that's what a solid-state recorder looks like in its final form. On the right, we have a different sort of view of that same stack. It's color-coded, and you'll see that in a second. But these are the elements of it that we simulate with our software emulator. The green block is the actual flight code that maps over from both these platforms without change. And then we have functionally and logically equivalent interfaces that are abstracted for the emulator versus the hardware implementation, but have the same access methods. And this is sort of a visual view of how you would use it. And again, the color coding from the previous slide carries forward here. So the green block is the actual data organization logic, the data organization software that will be incorporated into the flight system. The yellow are abstract interfaces that are specialized for use on the hardware or for use in the software emulator. So they have the same interface, the same function calls, but they are implemented slightly differently. And then on the left, you have the actual mission application software, which is using the solid-state recorder and commanding it to record and erase records, mission activities. So those commands are conveyed through this upper path into the data organization software control interface. And then also we simulate the data flows in this lower path to this unit here, which is a software component that simulates the actual recording and retrieval of data and simulates real-time access rates, things like that, to capture the aspects of this of data storage and retrieval. This slide tries to show a different view of how the software is implemented. So this is the data organization logic. I'm sorry. This is implemented in ANSI standard C++, both the data organization software that will end up in the flight model as well as the code used for the emulator. So this is that core data organization logic. It's a C++ class. It provides the API. Then we create a data organization simulator, which uses C++ inheritance mechanisms to extend that core functionality to carry it over and retain it, but then provide new interfaces for use in the simulation environment. And then we also include a third class, which is the data access simulator, which is a lower fidelity simulation of the actual recording and playback activities. But it, too, uses the same abstract interface of control commands and callbacks to the data organization software. So we have a fairly high fidelity simulation of the activities going on. So this class handles things like rate and capacity information, provides the memory control methods, callbacks, controls the simulation timing. That's a key element of it. Because ultimately everything ties back to the data rates flowing through the recorder, this element handles making sure that the simulation has some sort of traceability to that kind of real-time activity. So while this software structure is intended for implementing the flight data organization software in a PC simulation environment for very early integration, it also helps us with eventual hardware-in-the-loop testing of the system, because that same ability to specialize the interfaces to different environments can be done again for a hardware-in-the-loop environment where we continue to exercise the flight core software, but also start moving towards more realistic physical interfaces in a test environment. So simulation of the control interfaces. The data organization simulator object provides the methods for implementing the API calls that the final flight software will ultimately use. Those control actions are synchronized to the data flows via a discrete time simulation step. So as we run the emulator, there's a fixed time step. At certain times in that sequence of time steps, calls may be made to data organization software. Also during those time steps, data flows may flow into or out of the data storage unit. We can vary that time step very easily, which allow us to trade simulation fidelity versus runtime. So again, all of the internal data structures running in this emulator use actual flight software. So all the status responses, all the behaviors going back to the application simulation are as that would be seen in flight. So some of the key use cases here are to validate application command sequences, to make sure that the commands to record and transmit and erase data are actually functionally correct. We can evaluate changes to the API or that would help with that particular application, or consider command overlays, talk a little bit more about that later, that would, again, aid the integration of the solid-state recorder into the application. But because we are running in a PC environment, it's very easy to debug and test the software and fix any problems that might crop up. The other element of running the simulation is simulating the data flow. This is at a reduced fidelity. This tool is primarily intended as a means to exercise the API and allow the integration between the application and the solid-state recorder to start to be worked out at a very early time. But we do, of course, model the flow of sensor data as well. So we do that by just metering the quantity of data flowing into and out of the recorder without actually trying to store gigabits of data in our software simulator. So we model data flow as an aggregate amount of flow over an individual time step. So this includes modeling, or that aggregate rolls into the amount of data that's sourced or goes to the sink, the data sink, on that time step, as well as any flow control activity that may have happened. So all that's kind of bundled together and how much data moved in and out during this time step. And again, that time step can vary. Our simulations we have running most recently are looking at a 1 millisecond time step. So this is relatively small amount of data, fairly high fidelity. But as we do this, as we simulate the data flow, we exercise the software interfaces to the memory boards. So as in the flight model, the real hardware model, as data is being stored in flash memory, the flash memory boards are going to make requests to the flight software or to the data organization software for address updates to provide status information. So all of those interactions with the data organization software, those are actually happening in the simulation environment. And slightly reduced fidelity, but all those interfaces are being exercised. All the status state information is being updated appropriately. So we can use this to detect invalid data flows. So if the application simulation attempts to store more data than the hardware will ultimately be able to support, we catch that. We also do fairly high fidelity quantitative metering of how much data is stored. So this is the key element to looking at observation sequences and making sure that that will work out with how much data storage capacity we have in the recorder and our transmit opportunities, make sure that the mission's actually going to run correctly. So the key use case here is helping with mission design. So we can do things like explore scheduling mission activities, observations, concurrent observations by multiple sensors, which is a capability supported by the ultimate hardware SSR and the modeling tool, as well as data retrieval and transmission. We can monitor the data rates, the quantity of stored data to confirm the plan is feasible. That's not notional. We've already used this tool to help a client identify that there was a problem in their observation plan and that they were going to quickly fill up the data storage unit at the capacity they requested. It also provides additional instrumentation. So again, tying back with the application software, all of the API calls for status are available within the simulator. We have mechanisms to simulate or to visualize the status of the memory, and it's very easy to extend this with additional, using the C++ mechanisms to provide custom extensions for visualizing within the context of the application and for this early simulation and integration. So I have a few quick case studies of how this tool helps us in the development of the SSR designs for the missions very early on in the proposal phases. One case we're working through right now is extending the data organization software for multiple data stores. So the original design for this had a single large data store, so sensor data flowing in to several different flash memory boards, but all treated as one big file for each recording. We're currently extending this to provide totally independent management so we can store data from multiple sensors with independent control mechanisms. So we can use this, the emulator and the data organization software to move to this architecture here where we have multiple instances, multiple C++ instantiations of our data organization software running in parallel, talking to different flash memory resources, all within a single processor, and all using a common set of API commands. So we can prototype this architecture very early based in our software emulator to try and work out the details of this. Another way we're using this right now, another problem we're working through, is a case where instead of commanding the beginnings of recordings, the start of observations, instead of having that come from an application processor on board the spacecraft via the 1553 bus, for example, those commands to initiate recording are actually coming from the sensors themselves. They are embedded in a serial stream that will then carry the actual sensor data. This, again, is a change from our original architecture, but we're working on modifications to that architecture to handle that sort of sensor-level commanding, working that into our software. And again, we'll be able to test that in our software simulator very early, integrate it with the application, make sure we have most of those details worked out. And finally, a third case study of how we're using this tool. We're working on providing higher level control functions. So going back to the API, if you remember, there wasn't any command to, or the commands to read out data were record by record. So data is one record at a time is pulled out, transmitted, or part of a record. We have an application where it's desired to not attach to, for the application software to not need to keep track of those individual records, and rather just say, send the data oldest first until we run out of time. And so we are adding that capability with a software overlay that integrates with that stack you saw earlier through this diagram here. So the blue boxes represent the software overlay. It will interact with the existing API. So the software overlay will use the existing API calls. The native API calls will also remain available to the application software as it's needed. But we can add this additional functionality, and once again, we can code up this algorithm, we can integrate it with our data organization software, run it in the software emulator, exercise it against the intended application observation schedule, and make sure we're acquiring the desired functionality. So just a few conclusions on the approach. Again, this is by way of extended example, really it is a methodology for prototyping complex but encapsulated software components within a larger either software system or within a larger embedded system of a spacecraft. We use object-oriented design methods and language features to provide this test capability. So we use inheritance, we use abstract interfaces so that we can keep a very high-fidelity copy of our actual flight software, but allow it to be exercised in a different environment. Gives us the ability to do early test and debugging of this flight software, but probably more importantly, very early integration with mission planning activities. Exercise the software in the context of how it will be used and make sure it's going to do the job that it's supposed to. And also gives us the opportunity to quickly test out extensions that might support the application, ease its integration with its intended use, provide new capabilities. So that's end of the presentation, and I'm happy to take any questions.
Are there any questions? That's very cool. Sensor automated control.
Mike, how do you simulate timing? Are you using System C by any chance?
No, it's the timing simulation is custom coded for the simulator. Okay. So we have at compile time you can choose a time step, and then it is used to pace data flows.
Okay. Thanks.
So you mentioned there are 4 partitions. Is that just the why 4? Is it why not 6 or 5 or 7?
It is actually an entirely arbitrary number. It was a small power of 2. Actually, we do have an application we're starting to look at where there's a need for 16 partitions, and that is something we can easily support.
And does your software do like a concurrent record or playback?
Yes.
For multiple sensors?
Yes, it can. It can be extended to handle both concurrent recording for multiple sensors and concurrent record and playback, both happening at the same time for each of those sensors. Basically, in the final hardware implementation, each of our flash memory boards will support a simultaneous input and output stream.
How do you maintain the free space?
So erasure is actually separate from playback. So data can be played back repeatedly, and then it is erased on command. So in one use case, data would be erased as soon as it has been retrieved because it went to the transmitter and it's been transmitted to the ground station. But it is handled independently of record and playback. Did that answer your question, or?
Kind of like in ADA, do you maintain a link, pointer to say this is the beginning of the free space and? Oh,
okay. So as far as our usage of the physical flash memory resources, right. In the interest of wear leveling, we keep basically a first in, first out. Oh. And so data is written at one end and then erased from the other. So it's a simple two-pointer structure with the additional complexity of we are mapping around bad blocks. So within that flat memory space, we may have points where we are actually swapping in some other piece of flash memory to work around a block that has gone bad.
And your software detects failure. What sort of mechanism?
So in the physical flash memories, as we do accesses to program or to erase blocks of flash memory, there will be a flag that comes back from the actual physical component that will tell us if a block has gone bad. And so in the physical hardware, we're monitoring that. In the software simulator, we simulate those events, deliver that status information via the same abstract interface, and then that goes into the bad block remapping logic, which takes that bad block out of the usage pool, replaces it with another one that we've kept in reserve.
Just last, this is a software emulator, right? So would you say this is pretty much just checking out the functionality?
It is for testing the functionality of the software,
Right.
but also then for incorporating it at an early stage into the mission activities.
So it goes back to timing issues. So you have the higher fidelity of implementing that timing interactions.
So the timing is variable fidelity. Depends on you're trading timing fidelity versus processing time to run the simulations. It is not a sufficient tool for final end system timing testing, but initially, at any sort of fairly coarse level, it'll check out timing.
Okay. Thank you.
Additional questions? David. When you were, okay, I understand the concept of trying to wrap writes around on a device in order to wear level. When you slice it up into partitions, then some of those partitions might wear out faster than others, rather than having one complete. Did you do any trade studies or experiments to see if there was an advantage of the multiple partitions over having one big partition? And the second point is that with writing, that's where you run into contention issues on all sorts of data structures and things like that, and on these slow computers that we generally have to fly, contentions can kill your performance. So are your partitions there as in order to enable one task to write to one partition and another one to write to another, and then thereby do away with internal locking constructs?
Okay. Working through your questions in reverse order. No, we only support, while we have multiple partitions, only one record anywhere in the data store can be written to at a time. So you cannot be writing to multiple records, and even if they're in different partitions at the same time. And the second question, yeah, you're absolutely right that by defining partitions, you do create the opportunity to break wear leveling and to wear out areas of flash memory more quickly. So the choice to create a partition has to be driven strongly by an application need for that. Basically, an application that needs to have some sort of guaranteed reserve space for certain types of data when they arrive. This tool itself is really kind of intended to, on a case application by application basis, help to explore that. So it lets us look at under this application scenario, if we use this partition structure and have this observation sequence, how many times do we write to this partition, and is it a wear concern? So that's what the tool's for.
Maybe I missed this and you said it already, but obviously the flash in general is very slow and probably compared to those data rates you're showing up there, but are you doing anything like striping to optimize that, or are you not?
Yes, we exactly are. And so that low-level timing, managing the multiple flash devices in parallel and pipelining our accesses to them, because that is so fast, that's actually handled in totally independent logic that's running on FPGAs on the individual memory boards. And so that's a whole other technical area, and this software interfaces to a simplified interface to that control logic that's handling the much faster real-time operations.
So your hardware is handling the striping, or you're handling it in software?
The hardware is actually handling the striping.
Okay. And is there any type of redundancy handled in software, or does it support if you want to have mirrored copies or anything like that, or not in software?
Not in software, and really for the kind of rates we're often looking at, that's very difficult. I mean, the rates are so high, we generally lack the RAM to provide any significant buffering or any retries. Yeah, so you could have, yeah, and so the way that's been handled is if we need redundancy, we actually have multiple, it's redundant at the hardware level, and are seeing multiple copies of the data come into the data recorders.
Okay, very good. Thank you.
Thank you.